Okay, now the recorder's going. The question was about, have I graded the first test yet? I got the first one I got in, I got graded, but then I've gotten bogged down, and here's the situation. This week is the end of the first half of the term. Okay, this sometime over the weekend is midterm, right then. Okay, now what does that mean? That means for me, I have a first mini-term course, Physical Science 111. It ends later this afternoon. Today's the last day of class for that one. I've been trying to get, they have been turning in late work all day. I mean, all week and stuff. In fact, are you in that one, Matthew?
I'm sorry, say that again?
Are you in the Physical Science 111?
Yes, sir.
Yeah, I thought so. Okay, you'll know that today's the last day of class for that one. So I've been trying to get all those papers graded, and I swear they're coming in faster than I can possibly grade them. So that's why I'm behind grading yours. I've been trying to get all those graded because, and they've been coming in like crazy. Now, someone, Alondra, I think it was, who just came in. Okay, let me check that and make sure I'm right there. So as soon as I can get the first mini term over with, then I'll have a chance to get back to grading full-time materials. But I've had literally every time I sit down to start copying things that are coming in, they come in almost faster than I can copy them because of that class. People are sending in late materials, and it's just been hectic. And then too, and this is a problem on my end, and I don't know how to solve it. I'm in one room, the printer's in a different room, so it's a wireless situation. And there's something about our system here, especially late in the day, that doesn't work well. So I'll send something to the printer, and I will wait and wait and wait while it's trying to print. Usually I'm grading papers while I'm waiting for it to print, so I'm not just wasting time, but it just last night and the last few nights it's just been horrendous trying to get that done. So that's why I don't, another reason I haven't gotten everything graded. The printer has been so incredibly slow, especially late in the day. I don't know why. Maybe the signal gets weaker. I don't know. But yeah, as soon as I can get this first mini term over with, then I'll get to grading these others. This weekend is going to be, sounds like it should be, could be a rainy weekend. Maybe I'll get some papers graded because I won't have as much outside stuff that I can work on. So sorry about that, but yeah, I do. I'm pretty sure I have yours. Let me just check and see for sure. Um, uh, Already printed. I'm pretty sure I do. I have Terrell's research paper, Bennett's research paper, Terrell's first test, Kawan's first test, Victoria's first test, and Matthew's first test. So yeah, I have those, and like I say, I've already graded. I think it was James's. His was the first one in before I got swamped with the physical science papers coming in so fast and furiously. I've got labs and tests and everything in the world coming in with them. Kelly's coming in now. Let me get her marked here. Okay, there's Kelly. Okay, so that should get me up to 10 students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got them. All right, any other questions? Okay, for those who have just come in, an earlier question had been about, have I got the test graded? And I've got one out of maybe 5 or 6 that have been turned in graded. The problem is I'm trying to finish up grading my first mini-term class. They've had research papers. It's a big class, bigger than this one, about the same size as this one. Research papers, 9 labs, 9 tests, and a final exam. And for as many students are in here, it's about 18 or something like that. It's just, and all sorts of late stuff has been coming in last week and this week, so I've gotten way behind on grading other things, trying to get their grades caught up. So as soon as I can get this first mini term over with, I will be, here comes Bennett. Yes. Oh, absolutely. Like I said, I've only gotten maybe 5 or so in. So yes, as soon as you can get them to me, the better. Yeah. Just really need them before we get to the end of the chapter, okay? Because then I'll be giving you your second test. So, and we're moving along that way if we ever get started today. All right, good questions. Any others? Okay, then let me get the PowerPoint opened up here. And that also means I've got to move this taskbar out of my way. Move Azora out of my, I'm sorry, just kidding you. The names are over here on one side. And let me open the current slide. Okay. All right. Any other questions? For those who came in a little later, there was a question about whether I've got the test graded yet. I've got 1 out of about 5 or 6 that have been turned in graded. What's happened is we're now at very close to midterm. That means my first mini-term course is ending today, this afternoon. Oops, here comes Damien. Let me let Damien in, and then I'll save that and say it to him too. So first part of the alphabet is coming in very strong here. The last part a little bit weaker. So get those end of the alphabets in here. All right. An earlier question had been about the test. Has it been graded? I've only got like 1 out of the 5 or 6 that have been turned in graded so far. I'll take them anytime you get them to me, but one reason I've been behind in grading is that the first mini term is wrapping up this week, and I've been receiving this week and the end of last week just all sorts of back material. So that mini term physical science class had a research paper, 9 labs, 9 tests, and a final exam. And I've had the vast majority of that stuff come in the last 2 weeks. Okay, a lot of people were right on top of things, like Matthew was, and had things in early and on time, but a lot of people were not, and I'm still getting stuff in. I bet you after clearing out all my emails yesterday, I bet you it's full again today. And then I didn't quite finish clearing out all the things on Blackboard, but I made progress on that. But it may be Blackboard's fault. Things that I print off of Blackboard seem to just be very difficult for my system to take. They're very, very slow. So Blackboard may do something that screws it up. I don't know. But anyway, that's my sad, sad song. So you heard the violin in the background. All right. Any other questions before we get going today? Okay. Then, if there are no more questions, here's where we left off last time. We're in Chapter 4, Trigonometry, Section 4.7, Inverse Trigonometric Functions. And we were talking about the inverse sine function. Now, last time, they're referring to in this first slide both notations, okay? Here they list them. The inverse sine is called the arc sine, or I like this notation better, inverse sine. It's just that this is easier to write. The arc sine is 6 letters. This is 3 letters and a superscript, two digits there. So it's not much difference, but it's a little bit, okay? But these are commonly used in mathematics to remember the inverse sine denotes the inverse of the sine function rather than the reciprocal of the sine function. That's not, when you're dealing with any function and you put that -1 up there, that means inverse. When you're dealing with a number or a variable and you put a -1, that means reciprocal, which, by the way, is the multiplicative inverse. So it's still talking about an inverse, but that's strictly multiplicative inverse. With a function, you're talking about the function inverse. Okay. Now, if you recall, because sine is a repeating function, okay, repeating graph, there's only a limited domain of sine where it's 1 to 1, from minus pi halves to pi halves. Now, if you also remember what the an inverse function does, it flips the variables. Okay, so while the domain of a sine, the 1 to 1 part of a sine, is from minus pi halves to pi halves, the range of that is from minus 1 to 1. Well, the inverse sine, it flips it. The domain of the inverse sine is minus 1 to 1, and the range is minus pi halves to pi halves. So that's what's saying here. The values of the arc sine or inverse sine lie in that interval from minus pi halves to pi halves. Now, we came close to saying this before. I think I want to say it again. Okay, well, we'll get to it in a problem. I'll just hang off of that. The graph of the inverse sine function then is shown like this. Remember, the sine function starts at minus pi halves out here at a -1, goes up through 0, and then curves over and becomes a 1 at pi halves. This flips that, so this starts at x equal -1, the input, the domain, at -1, there the function value is minus pi halves, and here, whereas before, this is something you'll think this way more in calculus. Remember the sine function. Let me go back and show you the sine function. You're used to it, okay? If you think about it, the slope here of the sine function is 0 here and 0 here. The slope here really looks like and is very close to 1. Okay? Now, since you're flipping the input and output, what you have then for the inverse sine, you have an almost vertical slope here, not a horizontal slope, almost vertical slope here, almost vertical slope here, but here, again, it's almost 1. The slope is very, very close to 1 right there. In fact, right at 0, 0, it is 1. So that's how I help remember this. Whereas the sine function, the slope is 0, and it gradually goes through here, then it goes through 0, 0 at a slope of 1, and then comes up here and flattens out to 0 again. This is very steep out here at -1 minus pi halves, leveling off to 1 here, and then going to back to almost infinity. Basically, it is infinity there. The slope is almost vertical. Okay? So there's the graph. That's sort of things to remember in it. And remember, you flip your coordinates. Whereas the sine of pi 6 is 1/2, the inverse sine of 1/2 is pi 6. Where the sine of pi 4 is square root of 2 over 2, the inverse sine of square root of 2 over 2 is pi 4. So on and so forth. Now, that again gets me right on the edge of talking about how I think, this isn't necessarily what the book does, but how I think of inverse sine. Let's wait till we have an example, which first we have the definition. Let's do the definition. Definition of an inverse sine function. The inverse sine function is defined by y is equal to arc sine or inverse sine of x if and only if, these arrows go both ways, sine of y is equal to x. And that's exactly, or is leading to what I was going to say. This is what I do. When I see a function like this, I change it to an equivalent function like this and think of it that way, because I'm more used to thinking of sines than I am of inverse sines or arc sines. Okay? Now your x here is -1 to 1, because that's the range over here, that's the domain here. The range here is minus pi halves to pi halves, because the domain here was minus pi halves to pi halves. The domain of y is equal to inverse sine or arc sine is that the range is this, exactly the opposite of what domain and range is of sine function. And again, that's getting real close, and I think I'll go on and say it, okay? Because this statement is true. Now, the book doesn't like to use the terminology, I don't think. Modern thinking, for some reason, doesn't. But here's what I think. You take a trig function of an angle, right? Now, the book likes to call it a real number. But guess what? Those are angles, okay? That's what you take trig functions of. Those are angles. Pi halves, negative pi halves, pi 6, negative pi 6, pi fourths, pi thirds. All those are angles. Radians, sure. They could be degrees. It doesn't matter. But most of the time in inverse sines, we're dealing with radians, okay? Now, so what follows a sine is an angle. And what the answer of that is a number. This number is between -1 and 1. Okay? For your inverse sines are limited to minus pi halves to pi halves. Those are the angles. Here are the numbers, -1 to 1. So when you're doing an inverse sine, this is the number, that's the angle. So don't ever think you can take an inverse sine of an angle. You can't. You take the inverse sine of some number, which gives you an angle, which of course is a number itself, but it represents an angle. So that helps me to keep straight what goes where. Always when you see this, think this, just flip the things around, and this is your angle, that's your number. That means this is the number, that's the angle. Okay, I don't know if that's helpful for you. It is for me. So if possible, find the exact value of these things here. If I can find my pen, I will see if I can find the exact value. I found the pen, but I can't get it out of its tray, and it's a very expensive pen, so I don't want to risk damaging it, so hold on. Finally got it. Okay, I think I just went back a slide for some reason. Okay, now here's how I do this one. When I see this, I'll say, now, they like to use x's and y's. You know what I like to use? I like to use theta for angles and x, y, whatever for a number. Okay? So, I look at this and say the inverse sine or the arc sine of a number is equal to some angle. Remember, think of it that way. Now, I rewrite this equation into an equivalent equation. And that equivalent equation would be taking the sine of theta and saying that's equal to -1/2. What was your input here is your output there. What was your output here is your input there. Okay? Now, I ask myself, what angle theta, when I take the sine of it, gives me -1/2. Now remember, you have to stay between minus pi halves and pi halves. So don't go out here somewhere, don't go out here somewhere. Whoa, here comes Morgan. Let me get Morgan here, and we'll come back to that thought. Okay? Alright, that helps the bottom part of the alphabet there, but we're still missing a few. In fact, we've got pretty good numbers now. We're missing Jalen. We're missing James. We're missing Courtney and Sharika. Usually some of them come in a little bit later, I think. They're either at work or taking kids to school or something like that. So has anyone pondered that and thought, what angle theta, when I take the sine of it, do I get -1/2? Stay between minus pi halves and pi halves. Well, I'll tell you one thing, it's going to be negative. Okay? Anyone know what angle, when you take the sine of, you get a -1/2? Guess what? It's going to have a pi in it. What's the denominator? 6. minus pi 6. Buy that? Let's do the same thing here. I like to say this is the inverse sine, so you're operating on a number and you get an angle. So I like to call this a theta. The book like x's and y's, I get those crossed up. Which is the number, which is the angle? Theta, I know which is the angle. Okay, now I rewrite this and say the sine of theta is equal to the square root of 3 over 2. Now we want to stay between minus pi halves and pi halves. Don't go out here somewhere and don't go back there somewhere. What angle theta, when you take the sine of it, do you get square root of 3 over 2? Anyone know? Boy, you're supposed to know these. These are your friends, the ones you use all the time. I'll give you a hint. It has a pi in it. What's the denominator? 3. Pi thirds. Okay? Remember your little rule? Sine of 0 is 0. Sine of pi 6 is, sine of 0 is square root of 0 over 2, which is 0. Sine of pi 6 is square root of 1 over 2, which is 1/2. Square root of pi fourths is square root of 2 over 2. Square root of pi thirds is square root of 3 over 2. Square root of pi halves is square root of 4 over 2, which is 2 over 2, which is 1. Okay. To me, that's easy to remember. Maybe not. Okay. Now, what would you do with this one? Start off the same way. This is a number. You're looking for an angle theta. I like to do that. So this then translates, the other way to write this would be sine of theta is equal to 2. Do y'all start hearing alarms going off, bells ringing and saying, warning, warning, warning? You should. Why? What angle theta would give you a sine of, when you take the sine of it, you get 2. Guess what? There's no pi in it. This, if I could find my pen, where is it? Where is my pen? There it is. Okay. Does not exist. There is no angle when you take the sine of it, you get 2. Sine is always between plus and minus 1. So this doesn't exist. There is no angle in the world, and never will be, whose sine is equal to 2, or even 1.1, or negative 1.01, or anything outside of minus 1 to 1. Anything in between minus 1 to 1, yeah, there's an angle who has that as a sine. 2, no way. Okay? Now, any questions on that? Y'all are very, very quiet today. Okay? Let's do the A part. Let's see how they do it. Now, to me, maybe this is what I'm doing too, but it just seems like to me they're giving you the answer and saying that's the answer then. Okay? Because this is the answer, that's the answer. Okay? Maybe that's the same thing I'm doing, but at least to me, it sounds like a more reasonable approach to thinking through it. I said what angle theta gives you a sine, when you take the sine of it, you get minus 1/2, and that is minus pi 6. And maybe that's what they're intending you to do here, but it seems like they just throw it out there like, oh, here's the answer, and by the way, that makes this the answer. Okay. I don't know. I just don't like their thought process here. But you see, that's the answer we got to, right? Any question? Okay. The B part, same deal. They just say, because that's the answer, that's the answer. Okay. That doesn't seem like it makes any sense to me. I say, set that equal to theta, then say what angle theta gives you that, and that's where you come up with pi thirds. and maybe that's exactly what they're meaning, but just the way they write it seems bizarre. Okay? Any questions on that one? Same answer we got. Excuse me. I've been talking all morning and my throat is getting really sore. Let me see if a little carbonation will make it feel a little better. I don't know if it makes it feel better. It sure tastes good though. Okay, there's the B part. The C part. I don't know. They just say it's not possible. Okay. Yeah. Okay. We know that. And why? Oh, here comes Sharika. I knew she'd. Hope she'd be here. Hold on just a moment. Let me get Sharika marked present. I forgot to turn on my light. No wonder I'm in the dark here. This morning was very bright outside. I'm on the northeast corner of the house, but the sun's moved on from here. Let me, if I can, stretch over here and turn the light on. Okay, that sheds a little more light on the subject. All right, so again, I don't like their logic. It's not possible to do it, therefore there is no angle. Okay, and that's true. It's absolutely correct. Any questions on those three? Sharika, by the way, you just got here. We're in chapter 4, trigonometry, section 4.7, inverse trigonometric functions, and we're doing inverse sines right now. We just finished example 1, top of page 319. Was there a question? Okay. All right. And after every example, guess what? There's a checkpoint. Please do the checkpoints. Okay? Let's see if they do example 2. Well, they're not doing anything now. I have to click on the slide. Oh, remember that the domain of the inverse sine function is always between -1 and 1, so therefore 2 is way outside that. No solution. Does not exist. However you want to phrase that. Example 2 they're doing. Good for them. And this one you can go to larsonprecalculus.com and see an interactive version of this type of an example. So here they're saying, sketch a graph of that. Well, they just showed you one on the previous, 2 or 3 slides ago, but let's do the graph. Okay, if I can find my pen. Where are you, pen? There you are. Okay, so let's try to do a vertical axis here, try to do a horizontal axis here. We're doing y is equal to arc sine of x. Now I like to always think of this as sine of y is equal to x. I like to think in terms of the trig functions, not of the inverse. So I rewrite it this way. You exchange the x and the y. That's all you're doing. So y is the angle, x is the number. Well, the angles in that interval we're dealing with will be from -pi/2 to pi/2. So that's going to be what your y is, from -pi/2 to pi/2. And what are the numbers that come out of that? -1 to +1. Because that's what your x is. Sine of anything always between -1 and 1. Now, I may not have my scale very good, but we can live with that, right? Now, I flip things around. What is the sine of, say, when y is equal to 0? Where in the world is my pen? There it is. Okay. When you put a y is for 0, sine of 0 is 0, so 0, 0 is going to be my ordered pair. You don't know the order there. The y is 0, x is 0. Okay, when y is equal to, say, pi/2, x is equal to +1. So you're right over here. When y is equal to -pi/2, you're at minus 1. So you're down here. Now, here's the other thing I remember. When you do these this way, if you had plotted this horizontally, your graph would have been leveling off right at these values here. When you flip it, the reciprocal of 0 is infinity, basically. So basically, this graph here, rather than being almost horizontal, is basically vertical. But then it comes up here, and then remember they're both almost a one-to-one slope there, and then they go up to being almost vertical there. That's how it looks. Now you could throw in a few more points if you wanted to, like pi 6th. That would be 1/3 of the way up here. You should be halfway here, and we're pretty close to it. Minus pi thirds here would be minus 1/2 here. So it looks like we're fairly close to it. Maybe not exact. Okay. I don't like to do too many points. I get those and then remember my slopes. I think in terms of slopes. Of course, I've had calculus, okay, many times. So that's what I think of though. Any questions on that? So let me clear, if I can get my cursor here, my drawing out of the way so we can get to see how they do it. Okay, by definition, the equations y is equal to arc sine of x and sine of y is equal to x, exactly what I did, are equivalent equations. And here your y is going from minus pi halves to pi halves, so the x is going from minus 1 to 1. Okay, now that's why they gave it to you at x and y's. I would have preferred calling that a theta, but they gave it to you y. Okay, so the graphs are the same. I don't know what they mean by that. Yeah, okay. It's just that you're graphing the sine function vertically now, not horizontally. Okay. So they picked several points here. Fine with me. I like the minus pi halves and 1, the 0 and 0, minus pi halves and minus 1, 0, 0, and pi halves and plus 1. However, I can live with this one, minus pi 6 and negative pi halves and positive pi 6 and positive 5 halves. The others, I have a trouble, okay, I know square root of 2 over 2 is about 0.7. So I could do that one. That's okay too. Okay. So anyway, but now they've plotted yx table here rather than xy. So just remember everything is reversed. And when you plot those points, here's what you get. And that's pretty close to what we looked at. Pretty much a vertical slope here, a one-to-one slope here, and a vertical slope there. Okay, with these points, the important points here, those three, and then I like these two. They're pretty easy to do. This one's not too bad. You just have to guess where 0.7 is. That's, to me, negative 0.7 and positive 0.7. It's not as obvious where those points are. 1/2 I can sort of guess. That's halfway in between here, and negative 1/2 is halfway in there. And pi 6 is 1/3 of the way down here, negative pi 6, and positive pi 6 is 1/3 of the way up there. I can handle those okay. The pi 4th, yeah, that's halfway between here, but then to get a 0.7 here, I'm really guessing. So that's why I don't like that one so much. But it's perfectly fine. Any questions? Okay. Note that that is a reflection across the line y is equal to x of the black portion of this graph here. Okay. Now, I don't know if I can draw this in reasonably well, but remember pi halves is about 1.5. So let me see where is my cursor? There it is. Okay. And so this is about 1.5 here, negative 1.5. So that would be somewhere about maybe here. So this goes, get out of there. Goes something like this and like that. I have it drawn that well. It's a reflection across the line y is equal to x, because that's what you're doing. You're flipping the x's and y's. Okay. Now it says be sure that you see in the next figure, not this one, shows the entire graph of the inverse sine function. This is it. These parts out here, those are parts of the sine function, but they can't be used for the inverse sine because they're not one-to-one. This is the only part of sine that is one-to-one. So the inverse sine, remember that, okay, why are they doing that? The domain of y is equal to arc sine x. It's a closed interval minus 1 to 1. I don't know how many times we said that. The range is the closed interval minus pi halves to pi halves. Well, they didn't show the figure, did they? But anyway, oh, I guess that was the one we had already shown. Yeah, that one. That was figure. I can't read it here. Here I have a phone ringing. I hate to bother class, but I'm afraid this may be a student who can't get in the class, so I'm going to pause the recording. All right, that was the figure they were referring to. I can't see the figure number, but that's the one they're referring to. That's the inverse function of, well, now it won't advance, goodness gracious, of that. Okay, that portion there, the black portion. Okay, if I had drawn the other one in here, let's see if I can do that. Okay, that would have begun somewhere like here and gone up here. Here they almost on top of each other and do like that. So they are inverses of each other. Okay, was there a question? Okay, we've already done that. All right, now there is a checkpoint after example 2. Please do the checkpoints. Now let's look at other inverse trigonometric functions. A few we won't even mess with, but let's look at the ones that are most common. First with the cosine. Now remember, sine was one-to-one between minus pi halves and pi halves. Cosine is not. If you go between minus pi halves and pi halves, it's not one-to-one. It fails the horizontal line test. So for cosine, you have to go between 0 and pi. And that's the portion that's one-to-one. Notice the difference. The sine function was always increasing between minus pi halves and pi halves. The cosine function is always decreasing between 0 and pi. Okay? There's one difference. Shapes are pretty close. Okay? But the only part that's one-to-one is on this interval right here. So that's all you can deal with inverse cosine function. You take this, y is equal to cosine x, and do x is equal to inverse cosine of y, or the way they say it, y is equal to inverse cosine of x, which implies that, oh yeah, this is just two ways of saying arc cosine or inverse cosine, meaning the same thing, but both of these imply that cosine of y is equal to x. So again, I think these are my angles, these are my numbers. This is my angle, that's my number. This is the angle, that's the number. So this is flipped. Ooh, this is going to be messy to flip, isn't it? Okay? Because now your domain has got to be from minus 1 to 1, and your range is going to be from 0 to pi. But it's got to be decreasing, because this is decreasing. So this one's a little harder to visualize for me. Maybe you have no problem with it. Okay? So, oh, wow, they didn't even show it, did they? Shame. Okay. I'm pretty sure they do. Oh, okay. They wait until after they do the tangent. I think I'll just skip on over and let you see it. Here's an inverse sine. We've done that one. Here's what inverse cosine looks like. Its domain is -1 to 1, but its range is 0 to pi. But the pi is up here. This is -1 pi, and that's what the inverse of this is, pi -1. So this is -1 pi. Okay, and then it's 0 at its pi halves at 0, and that's because the cosine function was 0 at pi halves. And then this was the inverse function is 0 at x equal 1, and that's because, I'm sorry, because when you rewrite it and say cosine y is equal to x, those are equivalent. When y is equal to 0, x is equal to 1. So when x is equal to 0, no, I said that backwards. When y is equal to, no, I said it right. Y is equal to 0, x is equal to 1. So here's x equal 1, y is equal to 0. Yeah. Okay. So it seems like you're starting and going backwards. Okay. Whereas the inverse sine, you're starting over here and going up like this, and they correlate to each other. Here, this one correlated to this point over here. Okay, well, no, the point down here. So it's just, it's more awkward to draw. You have to think through the points and make sure you got it right. Again, notice infinite slope here, infinite slope here. Nearly a -1 slope there, just like the cosine was very close, and in fact it is a -1 slope. Where's my pen? Goodness, the pen just disappeared. There it is. Okay, a -1 there. This is a 0 slope here, a 0 slope there, a -1 slope here. So this will be, whoops, an infinite slope here, infinite slope there, and a -1 slope here. Okay, now, so there's the inverse cosine function. I wish they'd have shown the graph near this one. All right, similarly, you can define the inverse tangent function by restricting the domain of y is equal to tangent x to the interval -pi halves to pi halves. Now, again, I like to think in terms of, well, they've written it well here. Think of this. The domain of this is -pi halves and pi halves. That's where you can't. Notice you can't have a bracket here because the tangent of -pi halves and pi halves undefined. Vertical asymptotes. Okay, so you can't include that. So it's everything inside of that. So it's -pi halves to pi halves, exclusive, not inclusive. Okay. Now, therefore, the inverse tangent is going to have its range as being -pi halves to pi halves. It goes from positive to negative infinity. Why? Because the tangent of x goes from negative infinity to infinity. Okay, they don't show that graph here, but we'll deal with it. So the following list summarizes the definitions of the three most common inverse trigonometric functions. Don't mess with the rest of them. These will be basically all you need. Okay, y is equal arc sine or inverse sine of x if and only if sine y is equal to x. That's always how I do it. These are equivalent equations. And then think, what values can you use for what angles can you use here? -pi halves to pi halves, but those are your y values now because that's in the domain here, but it's in the range here. So that's -pi halves to pi halves inclusive. You can have those values. Your domain -1 to 1 because the range here is minus 1 to 1. Well, that's your x, which is your domain here, minus 1 to 1. Inclusive. Arc cosine, same thing, because cosine y is equal to x, but here you're restricted to y being 0 to pi. That's the close interval that is 1 to 1, 0 to pi here. Okay, and it goes from minus 1 to 1 here, inclusive in both of those. But the arctangent, y is equal to arctangent of x, if and only if tangent y is equal to x. What the y's you could take? Only from pi halves to minus pi halves to pi halves, exclusive. You can't evaluate them because at tangent equal pi halves, cosine is 0. And you can't divide by 0. Tangent is sine over cosine. So you cannot evaluate at negative pi halves or positive pi halves. Those are your vertical asymptotes there. So in your inverse function, they become your horizontal asymptotes. Okay? So the x, because the tangent value goes from minus infinity to infinity, goes up like that. Well, that's now your domain here. So your domain for inverse tangent is, now is that someone kind of get in, or am I just hitting? I guess not. Okay. So, because the output of tangent y is minus infinity to positive infinity, the input of your inverse tangent or arctangent is minus infinity to positive infinity, but your range is minus pi halves to pi halves. So here's the graphs. I guess it won't advance. Here's your inverse sine function. There's your inverse cosine function. And there's your inverse tangent function. Now, I'll try to draw you what the tangent looked like here. And this will be a terrible drawing. Understand that to begin with. Let me find, where in the world? Can you find my pen yet? Oh, there it is. Okay. So this will be going from here to something like here. This will be the tangent function I'm doing now. Let's pick me a different color for that. Do y'all have a color preference? Red. Well, I've used red. Yellow, green, blue, purple, orange. Give me a color. How about a purple? Okay, let's do purple. All right. So the tangent function would go something like this. If I can find my pen now. Where is it? Can anyone see where my pen is? There it is. I found it. Okay. There it is. Got it. Okay. It does something like this. Does like that. Okay. Sort of like that. I didn't come down here. They almost lie on top of each other here. This one goes infinitely high here where this is going. I'm going to go back to black for that one. This is going to approaching, whoops, approaches much more smoothly than that does. It approaches the horizontal asymptotes, never touches. These approach the vertical asymptote, never touch. Though my drawing looks like they do, but they don't. All right, any questions? All right, let's do example 3. How are we doing on time? I think we're doing all right. Yeah. All right. Now, how I start this is just like before. Arc cosine of square root of 2 over 2. Again, this is a number. I'm looking for an angle. So let's call it theta. To me, that's helpful. And this implies an equivalent equation would be cosine theta is equal to root 2 over 2. And I don't know why the pen does that. There's absolutely no reason for it. It just took off one direction, came back. Okay, I don't know. If I erase that, which I can, I'll erase pretty much everything. But I guess it's better than having ugliness there. Yep, see. And I don't know why this pen is, I think it's a sensitivity issue, and I don't know how to adjust that. Okay. So, what angle theta would answer that question? This is frankly a fairly easy one because both sine and cosine would be the same. Pi fourths. Okay? Because the cosine of pi fourths is root 2 over 2. And pi fourths is in that range from 0 to pi. Okay, arctangent of 0 is 0. What angle? No, arctangent of 0 is what? Well, let's call that some angle. This is the number. We're looking for the angle. Well, this implies that the tangent of theta is equal to 0. And I hope you know where that is. What angle is tangent equal to 0? Theta would also be 0 because tangent theta is sine over cosine. Where sine is 0, that's where tangent is 0. And sine is 0, 0. So that would be that one. Now, where is arctangent or inverse tangent equal to minus 1? Well, that's going to be at some angle theta, if it exists. What does that imply? That the tangent of this angle theta has to equal negative 1. You just flip if you do the inverse of the function, you flip the input and output. This is the output here, it becomes the input here. That was the input here, it becomes the output there, because this is the inverse function of that one. And what angle gives you a minus 1? I'll give you a hint. It's going to be a pi, and it's going to be negative. It really relates to something I said right up here. I said that the cosine and the sine were the same at that angle. Well, if they're the same, that means the ratio would be 1, but this is a minus 1, so that would be a minus pi fourths. Do you see that? Does it make sense? Okay. Let's go. Uh-oh, that's not what I wanted. These icons at the bottom of the page are hard to see. That's the one I want. Let's erase that ink and go. Excuse me. My throat's going out on me again. All right. Doing the A part here, rewriting this, I like to say equal theta. They like to say, because that's the answer, that's the answer. Okay, I mean, I'm making fun of them, but it really almost seems like what it is. It is true that because cosine of pi fourths is square root of 2 over 2, and pi fourths is in the domain, therefore that's the answer. But basically, it seems like they're giving you the answer and saying, so therefore it's the answer, rather than saying, what makes it the answer? Well, what makes it the answer would say, set that equal to some angle theta, and then the cosine of that angle theta is equal to that, and because then the cosine of pi fourths is that. So it seems like they just left off a few steps that were sort of necessary. Okay? Anyway, that's what we got, pi fourths. On the second one, the B part, again, they give you the answer because tangent theta is equal to 0 and 0 is in that domain. It follows that that's the answer. Okay, so again, it seems a little, but that's what we got to. Same train of thought, but it just seems like their way of approaching it is sort of bizarre. It seems like because we know this, you know that. Okay. And because the tangent of minus pi force, again, same deal, there is some angle whose tangent is -1. What is that angle? Well, it's minus pi force. So it's sort of like they're doing the same thing, but just the way they present it, it seems a little convoluted in some way. All right, now, by definition, the values of other inverse trigonometric functions, by definition, the values of inverse trigonometric functions are always in radians. Okay, I sort of alluded to that earlier. Here they state it unequivocally. They are in radians, not in degrees. No, I think more in terms of degrees, but once I get it in degrees, I change it to radians. Okay. All right. Now let's see. The last one we did was example 3. I think they're skipping example 4. Whoa, hit the wrong key again. Okay. I guess before that, okay, let's now do example 4 here. We'll need to go to the whiteboard. All right. First time we've used it today, so let me do the modifications on it. Get the taskbar that you can't see out of the way up here. Make sure y'all are as far out of the way. Yep, you are already. And then move the whiteboard as far the other way. Well, kind of the other way as I can. Okay. And up as far as I can. Yep, that should do it. All right. Here's example 4. I think I'm going to have to get my book in my lap so I can read it. Oh, I don't think we need the whiteboard. Use a calculator to approximate the value of each expression if possible. Now, remember that slide that I popped up there and said, well, really, they talk about this one later? It says here, by definition, the value, and I don't know what definition it is, but they want you in radians. So when you get your calculator, which for me right now is my telephone, okay, and I've got to log into it and go to calculator mode, which is here. Okay. Now, I've got to turn it sideways to get it in scientific notation. Okay. So, and it says right up here, RAD. That means we're in radian mode. If it didn't say anything, then I would hit down here. You see, here's DEG. That changes it to degree mode. If I press that DEG, notice the radian disappears, and now you're in degree mode. We don't want to be there. We want to be in radian. That changed to radian, so press that again. Now we're in radian mode. Be sure you're in radian mode before you do your inverse functions. Okay? So now what it says is arctangent of negative 8.45. That's what I guess I can write that down. What we're trying to do is the inverse. I'm going to write inverse tangent. It means the same thing. Of, and they put it in parentheses, which is pretty good, negative 8.45. Okay. Now, when I do this, I think, and it's not as necessary here, but I think in terms of that some angle theta, because this is an inverse tangent, so therefore this is your number, there's your angle. Okay, in radians, by the way, and this implies that the tangent of that unknown angle theta that we're looking for is equal to negative 8.45. Does that make sense? If that were sine or cosine, no it wouldn't. Okay, tangent or cotangent, because its domain is all real numbers, negative infinity to positive infinity, perfectly fine. But, so how are we going to do it here on our calculator? Okay, well, we don't need to think this part here. That's not necessary here. We could just enter this here. So what I'm going to do now, on my phone, I have to enter the argument first and then the function. If you got a good scientific calculator, you probably do the function first and then the thing. So I'm going to enter, and even in the number, I put the number first, 8.45, and then I have to negate the number with the plus minus key, and that gives me that. Now I take the inverse tangent. Well, wait, there's no inverse tangent listed here, but you see down at the bottom, you'll see a, no, I'm sorry, it's not at the bottom. Where is it? Okay, it's over here on the side. It says second. Okay, now your calculator may be different from this. Where is it? This is all backwards. That's why I'm having trouble seeing it. There's my RAD. There's my parentheses. I think that next key under that says second. Yeah, it does. So press the second key, and when you do that, notice what shows up at the bottom. Where it was sine, cosine, and tangent is now inverse sine, inverse cosine, and inverse tangent. So now that I've got negative 8.45 on my display, I hit the inverse tangent key, and that gives me where's my pen? It just was there, and now there it is. So that gives me theta equal to, or approximately equal to, because this is an irrational number, negative 1.453. I'm going to stop there. Okay? Hey, is that an okay number to have? Well, tangent, the theta can only be between minus pi halves and pi halves. Minus pi halves is about 1.57, negative 1.57. This is greater than that, so sure, this is in the right range. And since this is such a big number here, you're fairly close to that limit where things start going very, very negative. Okay, so that's what we get. What did the book get? Negative 1.453, and then they put some more digits in. So yeah, we're done. Okay, let's do the B part. The B part says, if I get on the right pad here, we want the inverse sine, and this time they use the inverse notation, which I like to use, of 0.2447. 0.2447. Okay, there is a decimal there, and this drives me nuts. You try to draw a decimal point, and it takes you out of that thing. Okay. Now, again, I'm still in the inverse mode here, so all I have to do, okay, not a bad idea to go on and think through this again. Say that's equal to some angle theta, which implies that the sine of that angle theta that you just defined is equal to 0.2447. Okay. Now, okay. Now, is that in the range of sine? Yes, it is. Sine goes from -1 to +1. This is less than +1, perfectly fine. So all we have to do is enter that 0.2447. Now, your calculator, you might be able to do the inverse sine first. This one I have to do the number first and then do the inverse sign. And when I do that, I get an answer of theta is approximately equal to 0.24721. I'll stop there. Okay. Now, time out a moment here. Let me point something out to you. If you remember, the sine and inverse sine right near 0 was almost 1 to 1. The tangent and inverse tangent right near 0 was almost 1 to 1. Okay? Cosine, not anywhere close. So therefore, a tangent or an inverse tangent, either one, and a sine or an inverse sine of a number close to 0 is not going to be off from that number very far. Now, negative 8.45 is not at all close to 0. So this answer is nowhere close to that one. But 0.2447, that's relatively close to 0. Look at this answer, relatively close to the same value, 0.24721. Yeah, it's different. They're always a little different, but they're going to be fairly close. For small angles, your sine in radians, sine of an angle in radians, very close to 0 is going to be very close to that same number, numerical value, and the inverse sine of a number close to 0 is going to be pretty close to that. That's for sine, inverse sine, tangent, and inverse tangent. That's just a little thing to keep in mind. If you're in degree mode, you're not going to get those kind of answers at all, and that's one way to tell when you need to get degree mode. So let's do the next one. The next one here is arc cosine, which I'm going to write as inverse cosine because I like writing that better, of the number 2. Let's say that's equal to some angle theta, which implies that cosine of that angle theta is equal to 2. Were you hearing any bells or sirens or seeing any flashing red lights? Please say yes. Why? Say that again. No such thing. There is no angle theta whose cosine is 2. You're absolutely right. This is no solution or does not exist. There is no angle that makes that true. Okay. And you'll find, oh, what if you did that on your calculator? They have the inverse cosine key there, so let's try it. Let's put a 2 and then do an inverse cosine of it. And guess what you get? Error! Okay, which means there is no such value. None. Nada. Not a 1. Hang it up. Okay. No solution. All right. There are checkpoints right after example 4, and then that's where the slide that we showed before is mentioned in the book. This one here that says, by definition, the values of inverse trigonometric functions are always in radians. I don't know what definition says that. The book is using that. But if you use the radians, then that rule that I said about sines, tangents, inverse sines, and inverse tangents close to 0, that will be true. It will not be true in terms of angles, of degree angles. Okay. Now, we move to compositions of functions. Okay, we got 3 minutes. Let's see what we can do in 3 minutes. Okay. Let me just get some of this stuff out of the way here. We know that for all x's in the domain of f and f inverse, the inverse functions have these following properties. Now this is going back to functions in general. A function of its inverse, the function undoes the inverse undoes the function, so whatever you put in, you get out. Or if you did the inverse function of a function, whatever you put into that function originally, your inverse function gives you that same number out. So this is the one and only time I want to say that the inverse function composition is commutative when these functions are inverses of each other. Okay, and then not only is it commutative, but it's always equal to x. Okay, whatever you put in, that's what you get out in both cases. So here are the inverse properties of trigonometric function. If x is between -1 and 1, and y is between minus pi halves and pi halves, then, now both of those have to be true. If they are true, then the sine of an arc sine or an inverse sine of x is going to be x. And the inverse sine or arc sine of sine y is equal to y. Now, I don't know why they changed the variables. They could have kept them x or made them both y's. Oh yeah, no, they had to because they put the limits up here. Okay, you can only take inverse sines of numbers. You can only take sines of angles, and those were your angles. So that's why they had to. Same thing with cosine, except the y's here are between 0 and pi, not minus pi halves and pi halves. X's are the same. So the cosine of an inverse cosine of x will be x as long as you're in this range. And the inverse cosine of a cosine of y, if you're in this range, will be y. Now, for tangent, remember that x can be any real number in the world, from negative infinity to positive infinity. So if x is any real number, but your y has to be between minus pi halves and pi halves, not including those values. Up here, yeah, you could include the minus pi halves and pi halves here, the 0 and pi here. You do not include the minus pi halves and pi halves here. Then if the tangent of an inverse tangent of x, that's the real number, you get x, and the arc inverse tangent of tangent will give you y as long as you're in that range. Okay? Now, I think that ran us out of time. So those inverse properties, where are we here? We're right here on page 322. And let me erase my mark on the next page so I won't be confused later. Let me put my paper in place. Any questions before we leave this? Okay, homework exercises here, starting on page 324. Any of the odds 5 through 17, they're all at Calc Chat. 5's at Calc View. Number 19's at Calc Chat. Any of the odds 21 through 35, they're all at Calc Chat. Oh, Azora has her hand up. What you got, Azora?
No, I have a problem. My CNA has expired. What do I need to do?
Okay. If you go to week 1 in Blackboard, you know how they break it up. Week 1, instructional materials, that's like the second tab under week 1, and go down to the very bottom of that. You'll see it says etc. Why they did that, I don't know. And I put down there the Cengage WebAssign class key for this course is, and it starts with Lawson.al space and then 4 digits and another 4 digit. That should get it to you. All right, good deal. Good question. I didn't know they lasted this long, but glad to find that out. So I said any of the odd exercises 21 to 35, they're all at Calc Chat. 21's at Calc View. I think you can do 37. It should be at Calc Chat. And I think we're going to be doing the rest of those after we finish what we do next. So hang off on that. We'll end there, pick up the rest of those next time. Any other questions, issues, problems, concerns? Okay, first I'm going to stop sharing unless you have a question on this slide. And I want you to have a good weekend, but I think it's supposed to be a rainy weekend, so it seems like a great weekend to do research papers, tests, or homework exercises, because we're getting close. When we finish, we're almost through with 4.7. When we finish 4.8, we'll have our second test, so it's a great time to get those first tests completed. And I'll try to finish grading at the same time. I don't know if I'll get it done, but I'm going to do my best to do so. Azora, do you still have your hand up, or is that from before?
My bad. I forgot to take that.
Okay, that's fine. That's perfectly fine. I thought maybe you had another question. All right, any others before we leave? Okay, we'll end the meeting for all of us. Have a good, safe weekend. I'll see maybe one or two of you later today. Okay, bye-bye.